Hello and welcome to today's webinar brought to you by Secure Thingz. Today we're going to cover IoT security and the use of secure MCUs and secure elements. As you can see, a packed agenda, so we're going to cover some of the security challenges and some of the objectives required in the IoT industry. We're going to talk about cryptographic methods, security technologies, secure elements and secure MCUs. So what will I learn? So you'll learn about some of the security objectives that we're looking to meet in the IoT world and some of the technologies that will allow you to meet those objectives. We'll look at the different types of secure device architectures and some secure device standards. The expected audience is engineers who are looking to develop an IoT product and managers who are looking to control this development of a secure IoT product. So let's look at some of the categories we'll be covering. Confidentiality. So this is a very important one and covers the whole process of encryption. This is about keeping data private and only accessible to authorized users. Here we're using AES type technology, RSA, ECC technologies, encryption, keys, etc. Non-repudiation. This is a very important one, especially in the banking industry. So this is about providing irrefutable proof of the validity and origin of the information. So the requirements to meet this objective is the capability to digitally sign documents and the use of hash functions. More detailed information about these functions is available in other webinars that are covered by Secure Thingz and available from our website. Trust. This is very, very important and is about the root of trust and identity of an IoT product. So in order to provide trust, a device must be able to authenticate itself and establish secure communication. Requirements here: we need to possess a unique identity and be able to prove that the device can communicate with other devices securely. Identity is the key for trust. And then availability. This is where a device must be able to maintain its function. So cryptography ensures these four key elements. Confidentiality, so this is basically sniffing is not possible, so the information is encrypted, and if a man in the middle is looking at the data, he cannot get at the actual underlying information. Integrity, this protects the data from modification. Non-repudiation we've covered, this is where the sender cannot deny that they sent it. And authenticity. So wrong data can be recognized. So these are very important factors that cryptography gives us in the IoT world. So let's have a look at some of the security objectives that we need to meet when designing an IoT product. So one of the most important ones is that we must allow for firmware updates and firmware updates over the air. To meet these objectives, we need to have integrity. So this is where we must be able to detect whether data that has been sent to us has been modified, and authenticity. So we must be able to prove who we are. So this is key to the identity of the IT product. Data integrity and identity. Of course, integrity is important there, and authenticity. Data confidentiality. So this is where encryption comes into play, and the data is encrypted, so cannot be seen by unauthorized users. Again, you need integrity, so you need to be able to check that the data is correct once received, and of course you need to be able to prove yourself. The non-repudiation comes into effect when you're looking at audit information. Transactional integrity, very important for financial controls, and anti-counterfeiting. So basically this is to show or prove that the information came from who you expected. And then for IP protection, we're basically just looking at encryption and decryption capabilities. So let's just look at some of the security technologies that are available to us. So one very important technology that's required is a true random number generator. This is the item that's used as partially to generate keys which can be used for encryption and decryption. It's very important that these keys are randomly generated. Key storage, another key technology that's available. This is basically secure memory, allowing us to hide private keys away securely in our hardware. Certificates, these are what give keys identity. Information on certificates is covered in other webinars on the Secure Thingz website. Ciphers, the encryption-decryption process, of course key to most security. And then hashing. This is a great feature that allows us to sign information and check that it is valid and not been modified. So let's look at some of the technologies that are available. In this webinar, we're just going to cover the two main ones, that is a secure element and a secure microcontroller. Now, a secure element, which is also often called an embedded SE, is a separate hardened processor core. It's linked to any mobile or IoT product via some sort of external interface, usually an SPI or I2C. It ensures that sensitive data is stored in a safe place and information is given to only authorized applications and people, usually to the connected microcontroller that's connected to the secure element. It's basically like a personal ID for the end user and the product itself. Now, often secure elements comply to certain standards such as the common criteria, which we'll cover a bit later. Now, a secure microcontroller is basically a standard microcontroller with additional dedicated security functions. These can accelerate encryption, decryption by having engines on board, and all of them should have a true random number generator incorporated on the device. Ideally, they also incorporate secure design architectures, isolating secure functions from main processing block. Some examples of this are the ARM Trust Zone and the Azure Sphere parts. Importantly, a secure bootloader allowing an immutable boot path is also a key requirement. Again, more detailed information on these technologies are available on other webinars from the Secure Thingz website. Here we're just looking at the different security systems available. So down here we have more consumer products such as mobile phones, tablets, etc. They generally have some sort of secure OS, Android, etc. running on them that has secure capabilities. Then we have cloud-based products, but importantly what we're looking at today are these two here, where we're looking at secure elements which are used in the enterprise zone and secure MCUs. The areas that we've got highlighted here in light green are what we are currently targeting at Secure Thingz with our tools such as Embedded Trust and C-Trust. More of that later. So let's look at some of the chip architectures that we can use when developing our secure IoT device. So we have 4 examples here. The first one over here is a large multi-core MCU which has multiple separated processors and is an extremely complex device. Then we have the fully integrated MCU, very popular, and also a lot of these are coming out quite regularly with more and more secure elements integrated into the MCU. Then we have MCUs that can have an associated crypto unit with them. We have a communications path here and the crypto unit, which may have encryption, decryption accelerators on board. Then we have an architecture which is including a standard MCU with no particular security options integrated into it, communicating with a very secure element, which provides the system device identification and cryptographic accelerators and other capabilities. So these are 4 example architectures of what your IoT product would probably look like. So let's have a look at these MCUs and architectures in more detail. So the multi-core secure MCU. So the advantage of this product is there are no external buses. So this ensures that there is no exposure of the secure data. It's kept within the silicon. It's hardware isolated security processor. In this case, the crypto processor is very secure and has been designed correctly to high security standards. There are extensive memory protection features because there are 3 cores here and are securely isolated from each other. There are cryptographic accelerators included. This allows you to have short key generation times, one-time programmable configuration areas, and this has limited attack vectors. Unfortunately, the disadvantages of such a large device and complex device is it is a higher cost, the software is quite complex, and there are a limited number of vendors today that provide such complex, secure microcontrollers. The integrated MCU, very popular and quite extensively available. Again, no external buses, so no exposure of secure data. Usually they incorporate lots of memory protection units, so separate secure and non-secure flash areas. An example of this is Trust Zone. Execute-only flash memory areas are sometimes incorporated. Flash array safeguards for tamper and unauthorized access checking, and a secure private key store, very important for allowing identity to be programmed into the device. Oftentimes they will have some cryptographic accelerators, sometimes limited. They will have unique chip identities, a silicon ID, and again limited attack vectors. Disadvantages are their slightly higher cost than a secure element, and not all the MCU secure features are available from all vendors. There is usually an assortment of the different secure elements on different MCUs. So here's some MCUs that are supported by the Secure Thingz toolset. We're looking at the SAM L11, the Renesas Synergy and RX products, and the ST microcontrollers STM32H7. Here we've just got a list of some of the security features available on these products. For example, Secure Boot is very important and available on all three. Other things like Trust Zone is only available on the SAM L11. Bootloader update capability, and down here we give you some dates of when these are to be supported. Let's look at the other option, which is a microcontroller plus a crypto unit. So the advantage of this is you can use a low-cost microcontroller. The unique identity can be implemented through an SRAM physically unclonable function. This is some code that runs and examines the SRAM of the device, and from that it can produce a unique ID. The secure key store is in the crypto unit with the device, which has tamper-resistant features. Also, these crypto units oftentimes have protection against physical attack. The disadvantages of this architecture are that the information is electrically exposed. This is between the crypto unit and the MCU. There are limited memory protection strategies on these low-cost MCUs. Additional memory, of course, is going to be required to implement the SRAM PUF, and not all the MCU security features are available from all vendors. Then finally we're looking at an embedded secure element. So the advantage of these are that they have a secure private key store, high tamper resistance, they can run applications internally ensuring very high security, often qualified to security standards, and designed to defend against a multitude of attacks. These are very hardened, robust devices. The disadvantages are their electrically exposed interface, again between the MCU and the secure element itself. There are often additional software drivers required to run on the MCU to talk to the device. There's limited memory to run applications on here, on the actual secure element, and one big limitation is you can only access a secure element through this microcontroller. Here are some secure elements that we are supporting with Secure Thingz tools. So you can see there is quite an array here, and there are some different features available on different devices. We've seen that the secure element has a lot more hardware countermeasures. and is more secure. So here's some of the items that are covered or implemented on secure elements. So oftentimes they have an active shield that covers the entire silicon area. You can actually see that here, and this disallows probing of the silicon itself, which can occur by some attackers on MCUs, where they can actually access flash cells. Data independent execution of cryptographic routines is often implemented on these devices, so that you can't actually see patterns in power consumption of the device, current used, etc. when implementing cryptographic functions. There is a scrambled bus inside the device preventing ion beam sniffing. The internal state is consistency tested. It has low voltage detection on the pins, which can be used to maybe access the device. It has temperature lockouts, internal clock generations, so that it is not susceptible to clock changes from the outside world. It has secure test methods. Oftentimes there's no identifiable die features or identification on the die, and also no package identification. These secure elements often are subject to standards. One of them is the common criteria. The common criteria structure consists of these three parts: introduction and general model, security function requirements, and security assurance requirements. So protection profiles define an implementation independent reusable set of security requirements for a category of target of evaluations. That's smart cards, firewalls, etc. Packages define reusable functional and assurance components, and security targets define a basic set of security requirements used as a basis for evaluation of an identified target. So these are the criteria used for common criteria standards. And here is a list of the different levels. So complying with EAL 1 means the device has been functionally tested. 2 is structurally tested, and as you can see, as we move up through these standards, the testing gets more and more rigorous. So here the whole device would have been formally verified, that's in the design, designed and tested fully by a third-party test house. So a quick summary of secure elements. So a secure element has been specifically designed to be tamper resistant. This is not fully the case for microcontrollers, of course, but the new Cortex M35P does introduce tamper-resistant features. Secure elements are usually compliant to security hardware standards. An example of this is the common criteria, which we've just covered. The secure element has the capability to run small applications internally, typically Java card applets. It has very fast cryptographic key generation hardware, which is very important. It can actually generate keys very quickly. It oftentimes has secure memory areas for storage of user data. It has simple hardware integration, and it has master-slave communication. So it does require a host MCU to access the functions. As for secure MCUs, they are very high integration. It's one of the key advantages of these devices. So you have crypto engines, crypto enclaves, and the MCU integrated into one device. Oftentimes they do have hardware tamper resistance, but it is somewhat limited, usually to simple pin detectors. There's no exposed communication interfaces because it's all fully integrated in the one package, so you can't see any data. Limited cryptographic functions, so key generation on these devices is often slow and limited. They do have secure memory areas for storage of user data, and of course they're very, very flexible. Lots of memory sizes, software and tools available. If you are interested in further information on IoT security subjects, please look at the Secure Thingz website, and here you can see some of the subjects covered by other webinars, application notes and white papers. Secure Thingz is an IAR systems company, and we deliver secure foundations for the IoT. We do this by simplifying secure design, secure provisioning and programming features are made available, and we enhance product lifecycle support. Thank you very much for listening to this webinar. As I said, if you want further information, please go to the Secure Thingz website. Thank you again and have a nice day.